like to talk a little bit about the various pieces between analog sort of signal processing, which would be sort of continuous time approach, and then talking about a digital signal processing approach and kind of looking at how these things fit. And kind of, starting with the assumption that there's some pieces of these transforms that may look familiar, right? Because for an analog signal processing part, you start off with a continuous time analog waveform. You go through some transformation. Let's argue we're going to do linear things here. And in this case, it's going to have some convolution to your y of t. Great. In the DSP case, you're going to have that x of t, but realize that it's then going to go through some sort of continuous to digital transformation. I'm going to get a sampled x of n. I'm going to assume that this transformation is ideal and going with a clock of n times some sort of sampling time, t sub s. And then I go through a discrete time transfer function, and then I get a discrete output, and then I do a discrete to continuous transformation where I may be sampling this. I probably need a clock to at least synchronize everything, and then I need to do some sort of smoothing, low-pass filtering in the output of it. All right, so that's great. And so you say, well, what happens if I want to make like very simple kind of computations, right? And this is how we want to think about this whole conversation. By the way, as we will look through this example, we'll talk about a TS of 0.7 milliseconds, which is then basically a sampling frequency of about 1.4 kilohertz. All good. All right, so now we begin to look at this. And we say, all right, now what would I look at? Well, let's assume a very simple circuit, a resistor and a capacitor. Now, this is, for some people may be familiar with, this is a low-pass filter, where I'd have an R and a C, resistance and a capacitance. You might think about this as having a time constant, because you may have heard of such things. And there's a time constant for this, which would then just be the product of these two components, which is 1 millisecond. And so the response I would get if I put an input step into here going from 0 to 1 volt is then going to give me a response like here to go to 0 to 1 volt out. I would express this mathematically as 1 minus e to the minus t over 1 millisecond, because that's kind of the time constant. And I get an exponential sort of convergence towards that equilibrium, and then times u of t. And you think, great, okay, that makes some sense. And for those of you trying to figure out how would I actually derive a couple of the properties out of this, you could actually write KCL at this node, and you would actually then notice that you would actually get c dv dt equals x minus y over r. I'm using x and y here to try to be somewhat abstract in these variables, also consistent with up here. These would probably be voltages, but probably voltages where you normalize as, say, like 1 volt. And so there you go. And so you put this together, you realize there's an R and a C right here. You multiply through, you get a tau. That gives you dy dt plus y equals x. This is sort of about as canonical a first order system as you get. X is an input, it's an arbitrary input, so you might imagine there's things you can do with this. One of which is, of course, if it's a step response in, which is u of t, this is the heaviside step function, goes from 0 to 1. If you had sort of 1 millisecond as your time constant, tau, because it's r times c, what I'm going to find out is that, oh yeah, in fact, I do end up seeing, I get this expression that derives out from this. And again, there's a whole conversation of Laplace transforms, which is the easy way to solve it. You can also take this solution and put it back in the differential equation, and if it is the solution, you know it's the solution. This fun thing about uniqueness of solutions. If you find a solution, it is the solution. So great. Also, since the Laplace transforms, where I could take this structure and take the Laplace of it, y of s and x of s, I could actually then say what is the Laplace transform of basically u of t, which is 1 over s, and then just solve, then solve it again. That works great. I could also ask what happens if I have a frequency input, and that's a frequency response. That would then take the s, make it go to j omega, basically removing the real part of the Laplace. And I get a response as h of omega, transfer function y over x is 1 over 1 plus j omega tau. You think, okay, this is good, right? So what do I see in the discrete form? What do I see when I do this as a DSP structure? Well, all right. what do I want to have in terms of this function? Well, assuming I have this is my sampling rate, this is my sampling rate, what I'm going to now look for is that y of n. I'm going to start off with this solution that I had here and realize that I want to get something that gives me the same sort of step response. So if I have a step response in, which I then can have a u of n, right, as a step response, I want to take that step response. And I'd like to get the same output step response when I'm done. That would make sense because that would look like I went through my continuous discrete conversion. Yeah, assume the step response just goes through. And then I should be able to look at this and I should be able to get the same sort of thing like I had here for this simple behavior. Let's see what we get, right? And so if I start with this, what I'd really want to say is, well, let me look at what I would get in the sample space. Well, imagine if I took this solution and just sampled it. Okay. Now I'm in a space where I say, fine, I can sample it at that level. Well, it's going to be n times tau, or ts, over tau. Well, what I really have here is I have a term, which is e to the minus ts over tau to the nth power, right? So I get really an a to the n where a is equal to this quantity. I did choose my variables carefully here. So a is a half. We'll do a few digits of precision. We'll go with a half. And so what this expression turns out to give me is y sub n is 1 minus 0.05 to the n times u of n. You think, okay, that's reasonable, and that's a very reasonable response I would get out of a difference equation system. And in fact, I can even say, well, what would that z transform have been, which kind of gives me an underlying idea of what the structure would be underneath. And what I find out of the z transform is that that's y sub n now actually gives me the subtraction of these two things, multiply them, sort of cross multiply things through, and I get 0.5 z to the minus 1 over the product of two terms. Cool, right? So from this, I could actually figure out what my difference equation is, which this would then be a second order. It's an IR response, but that's the kind of response I would see here. All right, great. And so then what I get after that is I say, well, if that's my step response, I often want to know what my impulse response is. And certainly discrete sort of things, impulse response often makes a little more sense than it does in the continuous space, at least for most people. And what happens then is you say, all right, what would it look like? Well, what is the impulse response, or what is the z transform for u of n? Well, it's a 1 over 1 minus z to the minus 1. And I realize, well, wait a minute, I already have it here. So I can just it just goes away. It's a very easy sort of a problem. So what's left is just the remaining two terms is the 0.5 and the 1 minus 0.5 with a z minus 1. So this gives me a very straightforward h of n, which is 0.5 to the n, u to the n minus 1, which is cool. It also gives me a frequency response. And I want to take a look at a couple of these questions. But one of the first things is, notice I take this h of n, it's just a series, right? Whereas a 0, then it's a half, then a quarter, then and all the way down, right? And so if I wanted to actually even use this like an FIR system, so instead I don't like the IR thing, I just want to get rid of some terms at some back end, I could probably get away with just, stopping about here, and that's about 2% accurate. If I stop here, it's better than 1% accurate. So I could just do that, right? And in fact, you can actually take a look at what are the different frequency responses I would get. And in fact, that's what's plotted down here. This is actually the frequency response of the continuous and the discrete, and then the continuous sort of inflected back into the discrete axes for you. And what you find is that the IR one, the IR and the FIR one actually agree very closely. There's a slight miss at the top, but otherwise they actually agree quite well all the way throughout the structure. You'll notice that the IR and the continuous time agree really well up to the peak and go all the way down to a point, but then stop. Now, to get a different perspective of it, you start to see, well, all right, what does it look like here? Well, they all feel very similar. There's a slight difference on the FIR, and the continuous time goes here, and the IR and FIR just kind of miss as I get close to pi, which is kind of at the upper end of the frequency range near where I'm sampling. And you think, wow, that's really cool. They really do agree really well. And so there's a lot of ways to kind of go back and forth with these concepts. And so you can kind of see the different pieces and parts as you put it together. And so it's really interesting, but I think in a way this kind of illustrates what was a phrase that Tom Barnwell, who was one of the sort of founders of digital signal processing early on, and sort of a little bit tongue-in-cheek here, but a fair point, is that he made this comment that DSP is a discipline that allows us to replace a simple resistor and capacitor with two anti-aliasing filters, an ADD, a D-to-A converter, and a general purpose computer or an array processor, as long as the signal we're interested in doesn't vary too quickly. And this kind of illustrates the point. You might ask the question, well then why would anybody ever do anything in a sampled form? And the simple answer is, well, it comes back to what is that general purpose computer? It is the programmability that makes all the difference. It is the programmability and then the ability for people to build infrastructure and so forth. And that turns out to be a really big deal, that you can sort of write code. Now, if you think about it, you go, but wait, could we not do analog in a programmable way? And the answer is, well, actually you can. And that's developed, and that begins to make this conversation get even more interesting going forward into the following years.